is Sean Carroll, and I brought this up here so I wouldn't mess this up. He is the Senior Research Associate in the Department of Physics at the California Institute of Technology. Here we go.
Thank you. This is working? You can hear me there in the back? Science is working? So it's a great pleasure to be here at Skepticon. When they asked me to come, there is a nice thing where they don't tell you what to talk about. You can talk about whatever you want. For me, it was easy because I have a book coming out next week, but you can pre-order it now if you really wanted to. It's about the Higgs Boson and the Large Hadron Collider and the search for this elusive elementary particle. But because it is Skepticon, I also wanted to give it a different little bit of spin here, not just talk about the Higgs boson, but put it in a perspective about where this is where the fundamental nature of reality part of the story comes in, how it fits into a bigger picture of what we know about the universe and what we will know about it going forward and how we make use of that knowledge. So I was fortunate enough to be there in Geneva on July 4th of this year at CERN, the European Particle Physics Center, where people camped out overnight to get into a couple of PowerPoint presentations early in the morning on July 4th. And of course, the reason why they camped out was because that these PowerPoint presentations from the two different experimental collaborations at this laboratory were announcing an amazing discovery, the discovery of a new particle, a new piece of nature, the Higgs boson. It wasn't just the people in the room or the people waiting. There were hundreds of thousands of people watching on live stream. I was actually there in a capacity as a journalist, not a scientist. And so I was in the journalism room surrounded by other journalists, even though I'm not a journalist myself. And when the announcement was finally made, the journalism room erupted into applause, which if any of you are journalists, you know that's not what you're supposed to do at news events as a journalist. But people got very excited. And so the question that you're allowed to ask is, what is the big deal? Why were people so excited about this? And what I want to do is give a very brief overview, not to actually answer the question, but to first convince you people were really excited. This was something that a lot of effort went into. So the Large Hadron Collider is the particle accelerator outside Geneva, under the ground. It crosses the border of Switzerland and France, that we've spent a long time building. It's the world's largest particle accelerator ever built. It's part of this CERN complex. And the numbers stagger the mind. So just to give you some of the numbers, it's 27 kilometers around. It's 100 meters underground. So if you're walking on top of the Large Hadron Collider, it looks like you're on a farm. There's hills, there's cows. Underneath, 300 and some feet, particle physics is going on. It costs about $9 billion to build the thing. It's hard to count because there's ongoing expenses and there's different accounting systems, but it's not very inexpensive. It's not a tabletop device. About 10,000 people are involved currently with the LHC. Inside this ring, you have protons moving faster than this. They're moving at 99.999999% of the speed of light, which is very, very fast. And to do that, you have 6,000 tons of magnets moving them around. The reason why the LHC and other particle accelerators are big is not because at every point they're accelerating the protons. There's only one point on the ring where they accelerate the protons. The bigness of the ring is because you have to steer them. The amount of energy in the proton beam at any one time is about the same as the kinetic energy in a freight train moving at 100 miles an hour. So you have 6,000 tons of magnets just steering the protons in this circle. And that takes, and it's all cooled to a temperature below that of empty space. If you were out there in the universe, the cosmic microwave background would warm you up better than being inside the magnets at the LHC. 275,000 kilometers of cable, and it could go on and on. It's a big effing deal, the LHC. And it was not easy to make it. You have to steer your equipment in between little streets in these villages of the mountains of France. You have to lower these magnets down with a few centimeters of clearance on either side into the tunnel. Once you start excavating a new tunnel for your experiment, you realize, holy crap, I'm in France, and that means that there are Roman ruins where I'm trying to excavate from the year 400 AD, and so I have to stop everything for 6 months to excavate the Roman ruins. And occasionally your accelerator blows up. So this is a picture of there was a terrible disaster just 10 days after the LHC first turned on, where one of the magnets blew up and it then spread to other magnets. It was put out in the news release as a leak, but if you had been standing next to it, you would have been dead, because it was actually several tons of liquid helium were explosively released into the environment. But, and here's the broken magnet afterward, but the CERN people working on the LHC picked themselves up immediately, did amazing technical feats, and got it all running. So there are two giant detectors. Atlas, this one that looks like a spaceship. CMS, that looks like some weapon of some sort. All of my references are from Hollywood movies, so that's all I can point to. And they're very big. To show you how big they are, there are people in each one of these pictures. There's a person, there's a person. These are not tabletop experiments. They would kind of fit into this room that we're in right now. They collide protons together. There's over 100 million collisions every second. And the amount of data that is actually kept from a collision is about a megabyte. So you can do the math. You're filling up over 15 million gigabytes of data being written to tape or to disk every year. And you say, well, a gigabyte is not that big. I have many gigabytes on my computer, but this is 15 million of them. So it's not just like there's a bunch of Macintosh, MacBook Pros hooked up. They've invented new ways to do the information collection and storage. Not every piece of the LHC is overwhelming in its size and awesomeness. This little thing that looks like a fire extinguisher is where all the protons come from. The protons come from hydrogen, which you then shake to get the electrons to leave the protons, and then you fill up the LHC. And there's 100 trillion, hundreds of trillions of protons in the LHC at any one moment, which is a lot of protons. But it's not a lot of protons compared to you and me. This little canister has enough protons in it to power the LHC for tens of billions of years. We don't have the funding to do that, but we have the protons. What happens, the protons smash together, and usually crap comes out. Just a whole bunch of particles that we already know about. Those are not interesting, and we throw them away. The overwhelming majority of data that is produced at the LHC is instantly erased, because we can't keep it fast enough. I say we in the sense that my friends, people who I know, the hardworking experimentalists at the LHC, have figured out what's called a trigger, to very quickly look at the events that are generated, decide whether or not they might be interesting, and if they might be, we keep them. So here's an event at Atlas. This is not a simulation. This is the real event. Protons smash together. A whole bunch of junk that is happily colored white comes out. But then also, these two little short lines are electrons, and these two long lines are muons. And they're extremely high energy, these electrons and muons, and that's exactly what you would expect to come out if you had made a little Higgs boson in your detector. The problem is, things like this can also come out even if you did not make a little Higgs boson in your detector. So there's a whole bunch of effort that goes into picking out the signal over the noise. Higgs bosons are created and they instantly decay. The lifetime of a Higgs boson is about a zeptosecond. I'm not going to tell you how short that is, but it's really, really short. You never see the Higgs bosons in your detector. They instantly decay into something else. And because of a little thing called quantum mechanics, you don't know what it's going to decay into. You can only talk about the probabilities. So we've used our theory to calculate the probability of the Higgs boson decaying into different things, bottom quarks and their antiparticles, W plus and minus bosons, etc. So we know what all the different possible things could be produced if you're making Higgs bosons. And then you go looking for them, and the problem is that all of these things can also be produced without making Higgs bosons. So what you're looking for is a statistical deviation from the predicted number of produced particles. You're not looking for a special kind of event, because every event there is can be made without Higgs bosons. You're looking for an excess number of events of a certain type. So often people say it's like looking for a needle in a haystack, but that's actually not right. It's like looking for hay in a haystack. It's like trying to verify there's a few more haystacks of a certain fixed length than you would ordinarily expect given the statistics of haystacks as you have experienced them in your life. Many, many highly paid and dedicated and hardworking physicists have set themselves to doing this problem, and here is what your $9 billion gets you. As I mentioned, I wrote a book about the Higgs boson coming out next week. You can pre-order it. Did I say that? The one plot that I had to fight to keep in the book was this. There's all these pretty pictures of, like, people and equipment and atoms and stuff. And they said, no, this is scary. You can't include that. And I said, we paid $9 billion for this. We should include it. They said, yeah, OK, that would work. What is this? This is a number of events that appear in your detector as a function of the energy of the event. And this is m gamma gamma. Gamma is, for some obscure historical reason, what particle physicists call photons. So this is just, you smash your protons together, you see two photons coming out with incredible energies. You use E equals mc squared to convert from energy and mass and back and forth. So you treat energy and mass as the same kind of thing. And then you say how many events are produced when the two photons coming out have, let's say, 110 GeV of energy. GeV is a giga electron volt, 1 billion electron volts. I'm also not going to tell you what that is, except that the mass of the proton is about 1 GeV. So we're talking about energies of our photons coming out that could not possibly be produced by protons at rest. There's not enough energy there. These are high energy protons. They're producing these photons. You make a plot and you see a bump. You might not have seen the bump if they didn't color in the helpful red line with the bump there, because the bump is very hard to see, but here's an arrow pointing to it. Look, there's a bump right there and there's a bump right there. Why are there two plots? Because there's two different experiments that do essentially the same thing. That is absolutely, absolutely crucial, as I don't need to tell anyone in the Skepticon audience. It's not enough to have one remarkable thing happen. You need to verify it. We need to test that you're on the right track. So having two experiments that do the same thing is what helps us believe that we're not actually cheating. So what you see is this bump, and what does that mean? That means that when your protons came together, it's easy for them to produce two photons, but if there was a new particle with a mass of 125 GeV, that particle would be produced and then decayed, and you get a few more events with a total energy of 125 GeV than you would otherwise expect. And that few other events, you can see how many more there are, a few dozen maybe, is the evidence that there is a new particle here with a mass of 125 GeV. So that is all just to convince you that we are excited. We have spent billions of dollars. Tens of thousands of people have devoted their lives to this. The LHC was first conceived in the 1980s and was first starting to be built in the early 1990s. So literally, people have devoted much of their professional careers to this machine to get these bumps. So you're going to say, who cares? Why is it worth $9 billion to build this incredible technological? I mean, it's impressive. When you go and visit, you will be overwhelmed. Was it really the best thing we could have done with our $9 billion? So my task is to try to explain to you the importance of the search for the Higgs boson. I haven't even really told you what the Higgs boson is yet. That will come along the way. But I want to admit, it is difficult to explain why the Higgs boson is important. Many of my friends are pulled up by reporters and TV crews and so forth. Please explain why the Higgs boson is worth $9 billion. And we haven't really polished our answers to that yet. It's gotten so bad that we invented a term that I'm not going to use here, but it's an attempt to convey to the outsiders exactly how important this new particle of nature is. We're going to try to do better than my friend Leon Letterman. Here's the secret. The Higgs boson is not all that important. That is a bit of a disappointment, I know, but it's only temporary. As you see, there's still plenty of space here. What's important is the Higgs field from which the Higgs particle is produced. And this is just as true for every other particle of nature. But the fact that it's the field that's important, not the particle, is only really crucial when you talk about the Higgs boson. So we need to explain quantum field theory. How much time do I have? Do I have another 3 months to talk here? Is that okay? So we're going to explain quantum field theory. It's a true fact of nature that when we talk about particles of nature, we're just being sloppy. Particles are not what nature is made of, despite the fact that we call this particle physics. What nature is made of is fields. And it's another remarkable fact that we don't tell you that as physicists popularizing our subject, we talk all the time about relativity. We talk about quantum mechanics. We talk about particle physics. We talk about string theory and the multiverse and the anthropic principle. But we're all thinking about quantum field theory and we don't tell it to you. So quantum field theory is the central organizing principle of modern physics. I can get by in my life as a physicist without telling it to you, but I cannot get by in my life as a physicist without learning it and using it all the time. Quantum field theory is the reconciliation of special relativity with quantum mechanics, and it is the best idea we have about understanding the world at a fundamental level right now. It might not be true, as scientists we always know, that there could be better and better approximations to how reality really works, but there's absolutely no experiment that has ever been done here on Earth that even hints that quantum field theory is not correct. So there's a lot of books on it. You could read those, or you could listen to the next 10 minutes when I will tell you what quantum field theory really is. So in some sense, a field is the opposite of a particle. A particle has a location. Here's a picture from a bubble chamber of tracks left by particles as they move through space. And you see that there are lines. There was a particle there, and then there, and then there, and then there. A field is the opposite. A field doesn't have a location. A field exists everywhere, and it has a value at every location. So a particle exists at one point, a field exists everywhere. And you are familiar with this. Here's a magnet. You can put iron filings around the magnet. They trace out the lines of something called the magnetic field. A magnet is something that has a field that extends all throughout space. And you've heard these words and you're familiar with them, but they are still kind of surprising. I like to quote my friends in the Insane Clown Posse. Am I allowed to say this? So they had a song that you may have heard. They can bleep it out in post. The Insane Clown Posse hip-hop duo with the clown makeup, they had a little song called Miracles that was explaining how miraculous everything around them was, and at some point they said the famous line, "Fucking magnets, how do they work?" We know how magnets work, so we were happy to explain that. But I want to stand up for my buddies in the Insane Clown Posse because magnets are still pretty awesome, okay? You know, you stick the magnet to a piece of metal, and it sticks, and you're like, all right, that's cool. But you have to understand, other sticky things stick because they're touching. You stick a piece of paper or stick a piece of silly putty or something like that, you touch it to the thing, and it sticks there. But if you put the magnet there, it begins pulling before it actually touches. How does it know that it's next to something it should stick to before it touches it? And the answer is that there's a field that you don't see it with your eyeballs, but stretching out in between the magnet and the metal, there is a field that is being affected by both the magnet and the metal, and it pulls things together. How does the laser pointer know to fall down? It's because there's a gravitational field. This was a really hard problem for a guy you might have heard of called Sir Isaac Newton. It's not just the Insane Clown Posse who worried about this. How is there action at a distance? How does the Earth and the laser pointer communicate? And now we know the answer. There is not a distance between them. There is a field that fills space at every point in space. There's a field called the gravitational field, and this is just responding to that gravitational field. At every point in space, there's a field called the magnetic field. At every point in space, there's a field called the electric field. At every point in space, there's a field called the neutrino field. There's a field called the up quark field. Every particle, every piece of reality that you've heard of is ultimately coming from a field. So quantum field theory says that literally everything is just some kind of wave in some quantum field or another. Here's XKCD. When we observe them, they become amber particles of grain. You've heard about waves versus particles, and if you took just enough but not quite really enough physics education, you know that there's this complicated question. Are electrons or photons, are they really waves or are they really particles? And there are many people in the world who've heard that question and still haven't known what the answer is. And the answer is they're waves. That's the right answer. It's not a debate. We know which is right and which is wrong. The world is made of waves. So why do we ever think that there are particles? That's the miracle of quantum mechanics. That's why it's quantum field theory, not just classical field theory. Quantum mechanics says that what you see when you look at the world is much, much less than the world really is. What the world really is waves. But when you look at it, you see particles. What the electromagnetic field is a wave, both electrical and magnetic, through space. At every point, there's some value of the electric field and the magnetic field. But when you look at it closely enough, it resolves into particles called photons. That's also true for all of the particles that make up this podium or the floor or you or anyone you like or don't like in the world. They are collections of vibrations in quantum mechanical fields. That's it for the whole quantum field theory lecture. I hope that was helpful. Why do we think this? Why is that the way the world works? Well, the very fact that we can make Higgs bosons by colliding particles together is evidence for quantum field theory being right. If it weren't for quantum field theory, you would describe the world as the individual particles. And the problem is, if that were true, you could tear apart collections of particles into their individual constituents, but that's all you could ever do. When you make a Higgs boson by particles colliding together, you're not releasing Higgs bosons that were hiding inside the proton. You are creating Higgs bosons anew for the very first time. How are you doing that? Because the quarks and the gluons inside your proton are really vibrating waves, and when they collide at high energy, they start another wave vibrating, and that wave becomes the Higgs boson. So the creation and destruction of particles is something that only makes sense if the world is really made of fields. Fortunately, it is, so we can make new kinds of particles. When we're making that Higgs boson, it's not, there's the conventional story is, it's like you take two wristwatches and collide them together and watch all the pieces come out. That's not right. That is very, very misleading. It's like you smash two Timexes together and a Rolex comes out. A whole new kind of thing is created when you do these high-energy particle collisions. So an example you can hold on to is if you play a piano and you just happen to have another piano sitting next to you, if you play a note loudly and you listen very carefully, the strings on the other piano will begin to vibrate. The note from one piano can travel through the air and it will affect the strings on the other piano, which will begin to resonate. Because the fields, which in this case are the strings of the piano, are connected to each other through some kind of interaction. So that's the world, as physicists understand it right now, a bunch of fields interacting with each other, transferring their energies back and forth. So to lay some science on you here is a Fineman diagram. And the way to understand what this diagram is telling you is to read from left to right as time goes on. You go from left to right. And there's sort of a particle-y language or a field-y language you can attach to this cartoon. There are gluons, the particles of the strong nuclear force that hold the quarks together. They can merge together to make a top quark, which then spits out a Higgs boson, which then decays into bottom quarks and anti-bottom quarks. But what's really, truly going on, I'm revealing to you here, is that these are waves in the gluon field. And they interact with each other and set up a wave in the top quark field. And that converts into a wave in the Higgs boson field, which eventually converts into the waves in the bottom quark fields. Every one of these particles that we see in our detector is just what quantum mechanics lets us perceive of the underlying reality, which is fields. So by using experiments, we've now been able to complete what we call the standard model of particle physics. And here it is, this flow chart. There'll be a quiz at the end, so take out your smartphones now and start snapping. So it's actually much more easy to understand what's going on than the flow chart. A glance at the flow chart would lead you to believe. There's only two kinds of fields in nature. Fermions and bosons are the technical terms. What they really are matter fields and force fields. The matter fields, the fermions, have the simple property that they only vibrate a fixed amount, which is interpreted in particle language as you can only have one particle in a place at any one time. The reason this podium is solid, the reason why it doesn't just collapse in on itself, is because the electrons in the atoms that make up the plastic molecules of this podium take up space because they are fermions. If you go through the flow chart, do you take up space? Yes, you're a fermion. Do you interact with a strong force? No, you're a lepton. Do you have an electric charge? Yes, it's -1, you are an electron. You could be a muon or a tau, but those would just decay into electrons pretty quickly. The boson fields can oscillate wildly. That's what they can do. They can oscillate as much as you want. That means in the particle language, you can pile bosons on top of each other. That's why the Earth can pull down this laser pointer, even though the gravitational field is so weak. The Earth is made of a lot of particles. So the gravitons are created in enormous numbers and can reach out and tug on the laser pointer. So if you pile on, you're a boson. Are you non-zero in empty space? We'll get there. What force do you carry? Gravity, you're a graviton. So those two kinds of particles make up everything that we have ever observed in any experiment ever done. That's a very impressive story. And I'm going to say that fact at least 2 more times just to drive it home into your head. Everything, every particle, every field, every phenomenon of nature that you personally have ever seen or heard or smelled or touched or tasted, I didn't include taste, but taste also counts, in your life is some aspect of the standard model of particle physics. In fact, if you're not a professional physicist, it's only a small fraction of the standard model that is even relevant. We have neutrons and protons that are made up of quarks. 2 downs and an up make up a neutron, 2 ups and a down make a proton. This is a deuterium nucleus, heavy hydrogen, 1 proton, 1 neutron. There's an electron moving around it. The quarks inside the proton and neutron are held together by the strong nuclear force gluons. The electron is held to the proton by the electromagnetic force photons, and the whole shebang is pulled down to the Earth by gravity. Those are the only ingredients you need to describe everything you've ever seen. If you're a professional physicist or an astronomer, maybe you've also interacted with some muons or neutrinos or something like that. Those are also in the standard model. So this picture right here is the 99% story of the universe, of your everyday life. Not of the universe, of your everyday life. The 100% story is the whole standard model. There's no experiment we've ever done that requires physics other than the standard model here on Earth. It's out of these particles, electrons, up quarks and down quarks, and the forces that hold them together, that the podium is made of, that I am made of, that you are made of. Every thought you've ever had, every person you've ever loved is a dance of these particles interacting with each other according to these forces. So, why do we need a Higgs boson? The whole point is that the standard model is enormously successful. It fits every experiment we've ever done here on Earth. Again, space is different, but here on Earth, the standard model reigns supreme. Why do we need the Higgs boson? Because without the Higgs field, the standard model would make no sense. It would not work. It would not fit the data. It would describe a world, but that world would not be our world at all. So here, this is the one slide on which you're allowed to get completely lost. I'm going to try, but if you get lost, I've given you permission ahead of time. The thing that makes, you're already lost? I didn't even start yet. Hang in there. The thing that makes the Higgs field different from all the other fields is that if you go out into empty space, if you make a little region of space out there in the interstellar vacuum, so it's as empty can be, there's no radiation, no dark matter, anything like that, and you make the minimum energy that the universe can have in that little cubic centimeter, and you say, well, what are the fields doing in that cubic centimeter? Well, all the fields are set to 0, right? If you make a magnetic field, if it's 0, it has 0 energy. If it's not 0, it has some positive amount of energy. And all the other fields work like that. So this cartoon on the left is trying to tell you, how does the energy change as I push the field away from 0? If the magnetic field or the electric field are 0, there's 0 energy. As I increase them, it costs energy. I need to put energy in to make that happen. So far, so good? Yeah, no, we have a tough crowd here tonight, folks. The Higgs field is different because the minimum energy thing that the Higgs field can be doing is not sitting at 0. If the Higgs field were sitting at 0, it would have more energy than it does stuck outside at some other value. The difference between the Higgs field and every other field in nature is that the Higgs wants to be non-zero even in empty space, even if it's lowest energy configuration. So here's a different plot. This is now space, and this is now the value of the different fields. You have all the different fields that make up nature, electromagnetism, quarks, gluons, etc. They're all almost 0, but there's small vibrations around 0. The Higgs field is not 0 in empty space. It sits out there. When you move through space, when you breathe, if you were a particle traversing between galaxies, you'd be moving through the Higgs field. You're not moving through any of the other fields. They're close to 0, but the Higgs field is everywhere. It's like the fish in the water. You don't notice it, but the Higgs field surrounds you all the time. The Higgs boson particle is a little vibration in that Higgs field. And what that does is that it affects the behavior of all the other particles that are moving through it. Every particle that you're made of feels that Higgs field. You don't notice it because it's just what you were born with, but there's a big difference between a world in which there were no Higgs field and a world in which the Higgs field is all around us. The elementary particles, the electrons and quarks and so forth, without the Higgs, they would all move at the speed of light. They would have 0 mass. Einstein says that particles can be massless like the photon or the graviton, but if so, they have to move at the speed of light. Fortunately for us, electrons do not all move at the speed of light, because otherwise you could not make atoms, for example. Without the Higgs, every electron would be massless and zipping by at the speed of light. With the Higgs, if you can see the Higgs in the background there, the electron keeps bumping into the Higgs field as it moves through space, and that gives it some heft. That gives it some inertia. It gives it some mass. And what that does is the Higgs field is kind of like Ritalin. If you imagine trying to organize a bunch of unruly kindergartners who are running around very, very fast, and you're trying to calm them down and have them do some interesting tasks, they're all moving at the speed of light practically for all intents and purposes. If you give them something that slows them down and lets them do interesting work, that's what the Higgs field actually does. It makes particles of nature slow down, join together, form complex structures like you and me. And what that means is that without the Higgs field, electrons would be massless. There would be no atoms. An atom happens when an electron joins up with a nucleus, and those atoms can join together to make molecules. But if the electrons are moving at the speed of light, they would never get stuck to a nucleus. They would just zip through space all by themselves. The world would be devoid of anything complicated. It would just be particles moving at the speed of light all throughout space. Fortunately, with the Higgs, everything slows down. You can explain atoms, you can explain molecules, you can explain everything we have ever seen in any experiment we've ever done. That is the significance of the finding of the Higgs boson. It completes a theory that is the complete theory of the everyday world. There's plenty we don't yet understand, but with the Higgs boson found, we now have a theory that is in 100% agreement with everything around us right now here in this room. Democritus would be happy. Democritus, the philosopher from ancient Greece known as the Laughing Philosopher, because he was laughing because he was like, ha ha, it'll take you 2,500 years to prove that my idea about the atoms is on the right track. Democritus had this idea that despite the wonderful variety of stuff around us in nature, it was kind of like Legoland. It's a wonderful variety of things made out of a few simple pieces, which he called atoms. And now we have his pieces, the standard model of particle physics. So, the laws of physics underlying everyday life are completely understood. And the reason why I emphasize this is because scientists, and skeptics for that matter, love to go right to the unknown things. There are many, many things that are unknown, from dark matter to quantum gravity to finance, okay? But there are also things that are known. And among the things that are known are how the matter around us in our everyday life actually works. And it's not just we have a theory that works. It's better than that. We know that there are no new parts of nature that we haven't found yet that could exert a substantial influence over our everyday lives. There are no new particles or forces that could be relevant to your everyday life that science hasn't found yet. And that's a much more dramatic claim that I'm going to try to justify just a little bit. So this guy, Ken Wilson, is one of the unsung heroes of 20th century physics. You might have heard of Albert Einstein, Richard Feynman, Stephen Hawking. Ken Wilson made an absolutely central contribution to our understanding of quantum field theory, because what he explained to us is that quantum field theory is organized by scales, by lengths. He perfected really what we now call the Renormalization Group. I'm not going to tell you what that is, but basically it's a way of saying, if all I care about are objects bigger than this, I don't need to worry about the details of what's going on distances smaller than that. This is what makes physics possible as a practical discipline. You don't need to know string theory to understand chemistry. You can understand how atoms work, and you don't need to know if there's anything that the atoms are made of. You don't need to know atomic physics to do biology. You can do biology in its own right if you don't care about the individual pieces it's made out of. You don't need to know biology to do economics or sociology or so forth. So this is a good way of thinking about the world, dividing it up into a hierarchy of scales. Wilson made it rigorous and mathematical in the case of quantum field theory. He said, let's think about different fields. They could have a different range. If they're very, very massive, they will be short range. If they're very light, they will be long range. And let's think about how strongly they interact with other fields. So you have a nice division into the upper right and the lower left. The upper right is the part of nature that is accessible to us. If things exist at long enough distances and interact with us strongly enough, we will notice them, whether it's quarks and gluons or electrons and gravitons. But you can hide things from us in quantum field theory, and we know how to do it. This is the important point. There are ways to hide things, but there are also ways to not be hidden. If something is long range and strongly interacting, if it's up here, we would have noticed it. There is no way we could have failed to notice it because we've done the experiments required to figure out what the quantum fields could be doing here, which means that the known knowns in Donald Rumsfeld's famous formulation are all up here in the accessible region. Both the known unknowns and the unknown unknowns are down here in the inaccessible region. There's plenty of room for new physics and surprising phenomena that we have not yet discovered. But what Wilson is telling us is that you don't need to know it to understand how atoms work, to understand how molecules work, to understand how the human brain functions, for example. And we can make this cartoon very, very specific. If you believe quantum field theory, and of course you might just disbelieve quantum field theory, you might believe all sorts of things. But if you believe quantum field theory, which is our best tested physical theory of all time, then there are tight constraints on what new kinds of particles can exist. You might say, well, how do you know there's not a Zillbot particle that you just haven't noticed in your experiments yet? Maybe the Zillbot is very important because it comes in and it interacts with your brain and gives you thoughts and free will and feelings, and then it goes on its own way. Maybe you've heard people say things like that. So that has meaning. All of these statements can be analyzed in the framework of quantum field theory. You're saying, here's a proton, it's moving from left to right. Here's a Zillbot, spelled with an X. It comes in, it interacts with the proton, and it goes on its own way. That is what you are proposing. You might not be meaning to propose that, but if you're working within quantum field theory, this is what you mean. You mean there is this Feynman diagram, this new particle, this new interaction. And it is a rule of quantum field theory that I can take these diagrams and I can rotate them by 90 degrees and get another diagram that is real. So I can rotate this. I just take the bottom and move it to the left. If this interaction exists, then I can smash protons together and create Zillbots. If it's a strong enough interaction that it would have any effect whatsoever on your brain, we would have made it before in a particle accelerator, and we have not. So Zillbots could exist, but they cannot both exist and interact with you strongly enough to be interesting if you're a person other than a particle physicist. So we've looked. There could be plenty of new particles of nature, but they must be either weakly interacting, too heavy to create, or too short-lived to detect. And what that means is they can't possibly be very relevant to your everyday life. They cannot affect your consciousness. You cannot blame them for being in a bad mood. You and everyone you know is made of the standard model of particle physics and nothing else. Likewise, could there be new forces of nature? And the answer is yes, of course there could be new forces. But again, what is the range of the force? What is the strength of interaction? We have looked. This is an actual photograph of an actual experiment looking for new forces of nature over distances of about that big. And we know what they could interact with because we know that you're made of protons, neutrons, and electrons. So you just have to ask, what forces are there that interact with protons, neutrons, and electrons? And the answer is we haven't found any. So if there are any, they better be either very, very weak or very, very short-ranged, like smaller than an atom. And therefore, they're not going to be relevant to your everyday life. You can't blame your stomach ache on the new forces of nature, and so forth. And again, fearsomely quantitative results. Here is the actual experimental version of that cartoon I showed you of Wilson's ideas before. Here's a range of a force, strength of an interaction. We've ruled out every possible force that is both long range and strong enough to notice. If you go to the numbers here, this is the length in meters. So this is about 1 meter, about a centimeter is down here. And you look up here, the strength relative to gravity. The constraints are that any new force over that range has to be 100,000th as strong as gravity or weaker. Gravity is really weak. So gravity is up here, it's the green arrow, right? So if there's some new force of nature that interacts over this kind of length scale, it's much, much weaker than gravity is. And the gravitational force between you and me is utterly, utterly irrelevant. Therefore, if there are any new forces of nature, which there might very well be, they don't affect your everyday life. Just to convince you that gravity is weak, I have a picture of people overcoming the force of gravity through a discipline called yogic flying, where you sit on the mat and you concentrate really hard, and you fly. You levitate up into the air. It helps if you jump also, but you can overcome the force of gravity just through the electromagnetic interactions in your muscles. You are very small and the Earth is very big. The Earth is exerting gravity on you, and you are overcoming it with your neurochemical influences that makes your muscles twinge. So any new forces must be weaker than gravity, and gravity is nothing. So any new forces of nature are not going to be relevant to your everyday life. So that's the conclusion. The conclusion is that as far as the immediate world of our experience is concerned, as far as what you see and touch and taste and feel as you go through your everyday life, we have the theory. We're done. That does not mean we understand everything, but the underlying laws that describe what baseballs are made out of, or tables, or living beings, we understand them. It's electrons and quarks with masses from the Higgs field interacting via those forces. That's the everyday world. And now, from experience, I know that 2% of the people in this room are going to wildly misunderstand what I'm saying and think that I'm claiming that all of physics is done. Even though I've already said 3 times, I'm not saying all of physics is done. So, for the 4th time, all of physics is not done. There's plenty that we do not understand. This is what I do for a living. I think about the parts we don't understand. Dark matter, dark energy, the origin of the universe, quantum gravity, unification of the forces, and that's just within high energy physics. There's also the rest of the world. Once you know that the world is made out of electrons, protons, and neutrons, you are not done in terms of understanding it. What about chemistry? What about biology? What about sociology and psychology? There's an enormous amount of effort still to be done in understanding how the world works. My point is, we know what the ingredients are. The analogy I sometimes use is it's like chess. You can learn how to play chess, which means you know what the pieces do. You know what the pawn is allowed to do and what the knight is allowed to do, and so forth. Guess what? That does not make you a good chess player. There's still a lot to learn after you've mastered what the pieces do. So when it comes to for the everyday world, we have figured out what the pieces are and what directions they can move in. That does not make us good world players or chess players. It does constrain the kind of games you can play. If someone has come up with a great new chess strategy that involves the rook moving diagonally, you know that you can rule that out without listening to their elaborate presentation on it. Likewise, if someone has a great new theory of living their lives that involves homeopathy or astrology, you can tune them out without listening to the details. Because just knowing the fact that the standard model of particle physics is the right theory of the matter that makes up the everyday world is immediately enough to rule out a whole host of possible phenomena. Anything you can't do with electrons, protons, neutrons, gravity, and electromagnetism, you can't do in your basement. At the LHC, you can do it. But here in this room, you cannot. You cannot bend spoons with your mind, unless your mind tells your other arm to go out and bend the spoon. But you can't just do it with a new force that is emanating from your cortex, because there are no such forces. You cannot predict the future, see around corners, the position of Saturn when you were born, sadly irrelevant to the rest of your life, blah, blah, blah. And in fact, we know that there is no life after death. Sometimes even atheists and skeptics like to be open-minded about this because we haven't done all the right double-blind experiments, blah, blah, blah. Forget it. If you believe in life after death, tell me what particles contain the information that moves your soul from place to place. Is it electrons? Because those would be easy to notice, because electrons are electrically charged, and it's actually quite a lot of charge. Is it atoms? But the atoms don't move very much when you die. If you believe that there's some way that you have an immortal soul that travels from place to place, then you are not just saying we don't know how it works. You are saying that our current knowledge of the laws of physics is wrong, which means you better give me a good reason to believe that our current knowledge of the laws of physics is wrong, because it's not, and I'm going to move on to do more interesting things. So, to bring it back to where we started, I want to emphasize the world is a really big place. This is a picture of, from the Hubble Space Telescope. So this is the Hubble Ultra Deep Field. If you take your camera and you point at the sky, at a blank, empty region of the sky, and you push the button, you leave the shutter open for a long time, if your camera is attached to the Hubble Space Telescope, this is what it will see. You will see that what you thought was a blank region of the sky is alive with these little blobs of light. And every one of those blobs of light is a galaxy, much like our own Milky Way galaxy. So we live in a galaxy with 100 billion stars. Every one of these little blobs, even the tiny ones, are galaxies with about 100 billion stars. And there are about 100 billion galaxies in the observable universe. There's also the unobservable universe. There's also the things in the universe that we don't observe, like dark matter and dark energy. We are very tiny, and the universe is very big. Just to drive that home, here's us. It's very bright in here, so you can't see it. This is the pale blue dot image. This is the photograph that was taken by the Voyager 1 spacecraft when it was 4 billion light years away from the Earth, and Carl Sagan coaxed NASA into turning it around, taking a last picture of the Earth. It takes up a pixel or two in this image. We are really, really tiny, and the universe is very, very big, and there are many, many things we don't understand about it. But almost 50 years ago, theoretical physicists sitting around trying to figure out how the world might work, predicted that there was this thing called the Higgs Boson. Knowing what we knew about nature as it already was, we could figure out that the best possibility to make sense of the whole shebang was to invent a whole new kind of field that no one had ever seen before, and make very explicit quantitative predictions about what it would be like. 48 years later, $9 billion, 10,000 people working hard, we found the thing. We are very tiny, we human beings here. We're very tiny compared to the universe. There's a lot we don't know, but we are able to figure things out. We are able to stretch our intellect over billions of light years and many, many years, figure out how the world works, and it's a lot of fun to keep going. That's the big deal. Thank you.